A dynamical system can exhibit high variance while every transition remains reversible. It can also exhibit zero variance while being completely irreversible. These are not the same property. They do not imply each other. Uncertainty is about the spread of reachable states at each step. Irreversibility is about which transitions are structurally forbidden. Models break when one is treated as evidence of the other. The wrong diagnosis produces the wrong intervention. Variance is defined on the distribution of outcomes. It measures the spread of states reachable over time, a statistical property. Forbidden transitions are defined on the transition matrix itself. Specific state pairs where the transition probability is exactly zero, a structural property. High variance and forbidden transitions are defined on different objects. Changing one has no necessary effect on the other. The two dimensions are formally independent. 4 combinations are possible, and all 4 exist in real systems. A deterministic cycle is reversible and certain, low variance, all transitions allowed. A random walk is reversible and uncertain, high variance, all transitions allowed. A ratchet is irreversible and certain, it moves in one direction with no variation. An absorbing Markov chain is irreversible and uncertain. Absorption is eventual, but the timing is random. Each requires a different analytical framework. Treating all 4 as the same class produces systematic errors. Diversification is the correct response to uncertainty. Different outcomes offset each other in expectation. Spreading exposure reduces expected loss. Against irreversibility, diversification does not prevent absorption. The absorbing state is reachable regardless of how diversified the exposures are. The structural constraint is not on the distribution of outcomes. It is on the transition architecture, which states can be left and which cannot. Maintaining structural slack from the boundary is the intervention that changes absorption probability. A hedge is designed to pay out when the bad outcome occurs. This is appropriate when the bad outcome is uncertain. It compensates for realized loss. When the system reaches an absorbing state, the hedge may pay, but absorption has already occurred at that point. The hedge addresses consequences, not causes. Preventing absorption requires action before the absorbing boundary is reached, maintaining structural slack while exit is still possible. No hedge provides that. Managing uncertainty and managing irreversibility are different optimization problems. Hedging minimizes expected loss under a distribution of outcomes. This works when the loss is proportional and the bad outcome is probabilistic. Reducing absorption probability requires knowing the transition structure, monitoring distance from the absorbing boundary, and taking action to maintain slack before the threshold is crossed. These are structural interventions, not statistical ones. Uncertainty management tools are locally optimal for uncertainty and structurally inadequate for irreversibility.